Okay, guys, I have another video. I want to sort of walk you through a demonstration of standing waves on a string. So in, I think it's chapter 17, and in the notes that I've uploaded, we talk about how reflection is a way to build a standing wave. And it's not because reflection is crucial, it's because we have to have counter-propagating traveling waves, right? We developed a mathematical framework for understanding wave motion, and we developed that framework to understand how a phenomenon travels through a medium, right, without moving the medium itself, just by transporting energy through it. So we need to have counter-propagating waves, and one way to do that is to send one into an interface that reflects it back. If I have a continuous source of wave excitation, my reflections can constructively interfere with the original, you know, in my perspective, left to right, and your perspective, right to left, propagating wave. So I have those two waves interfering, and I can produce a standing wave pattern where I no longer see anything that appears to be traveling. I just see something that appears to oscillate back and forth in place without moving left or right. So we're going to do this on a string, right, which is how we had developed the idea for our wave analysis. And our mechanism, our apparatus, is a string fixed at one end. It goes over a pulley, but you can see that the string is not moving up or down. So as far as its transverse behavior is concerned, it's fixed. You can kind of see the string oscillating there. And then down here, we have taped to that track, because I screwed up the clamp, an oscillator. It's a blade that wiggles back and forth. So we have to talk about our model a little bit. The truth is, we have a string, our medium, that's fixed at one end. So we have the pulley. We can just say, oh, the string is not moving up or down, so let's call that a fixed position. It's true that the pulley itself will actually wiggle a little bit, and that becomes an issue if we hit a resonant frequency for the pulley system, and it'll start to rock back and forth. But to a first approximation, we're going to ignore that and just say the string is fixed at this end. So before we excite it and neglecting its sag due to gravity, we just have a string. Okay, what about this end? Well, we have the oscillator, the blade. And technically speaking, that blade is going up and down. All right, but that's not what I really want to study. That blade is going up and down by a very, very small amplitude compared to the amplitudes of the transverse motion of the string that we're going to see. So strictly speaking, I should say, look at a system that has one fixed end and then a tiny little oscillation here that's going to drive a much larger oscillation further back in the system. But what we're going to do is just say, let's call that end fixed too. So we're going to say both of these ends are fixed. And this is a cop-out to deal with the fact that we don't just have a string between two fixed points. We have a string between one kind of fixed point and one point that is actually flexible and moving and is itself part of the system. But we didn't exactly study how to deal with that more complicated system. We could. It's not that complicated. It's a leaf spring, essentially. We could model that too. But it's really a coupled pair of oscillators, and we don't want to explore the math behind that just right now. It would actually fit in pretty well in the stuff we were doing in the first part of the course. But we're going to ignore that and just say, let's consider the system to be fixed at two ends, and an unstated mechanism, which is the oscillator, is going to drive energy into this thing and excite the various modes that can persist as standing waves. So we could have the fundamental, right, where we have a half wavelength, and this just goes back and forth. So you get kind of an envelope effect, right? But it doesn't appear to move left or right. We could have a higher order mode too. So this is a half wavelength, fit into L. We could do the next highest order, which is to have a full wavelength fit into L, right? And this thing just oscillates back and forth. Pardon the crappiness of this drawing. And we could keep going. So this is a lambda wavelength matched to L. We could have the same L, but have 3 half wavelengths, and so on. We could just keep going on and on and on. All right, so I said before that what we need to do is generate wave excitation on one side of our system and have it propagate in, and then have another wave excitation propagating in the opposite direction, and we can generate an interference pattern. what we have to do is kind of time ourselves, right? So imagine that you're throwing a baseball at the wall, and it goes gadunk and bounces back, and you catch it. But each time you're going to catch it with your hand right there, you're going to turn around once or something like that, so that you synchronize your motion up with the ball coming back to you. We have to synchronize two different things. They're generated at the same frequency, so that helps us a little bit here. But we have to tune some parameters to get that sync to happen. We could change the length of the string. That would work. We could change the frequency of the oscillator. That would work too. But I don't want to fuss around with changing the length of the string because I have it set up semi-rigidly, and I don't want to change the oscillator because we bought one and it oscillates at just one frequency, right? It's not tunable. We can try this again with a tunable source, but who cares? It's not important. We can do another thing, which is to change the speed at which the wave is propagating through the system. So that's the one we're going to do. We could change any of these knobs to change the behavior that we observe, but what we're going to do is change the velocity. So just before spring break, we analyzed a bunch of wave equation stuff, and we found that the speed of sound in this medium on a string is the square root of the tension T divided by the mass density mu. So mass density is how many kilograms per meter does the string mass. Tension is just the tension force in the string. So if we were to increase the tension, we would increase the velocity of a wave on the string, right? If we decrease the tension, the other effect would happen. We could also adjust the mass density. I can't really tune it in the same way because it's not like I can look at a string and change it and say, now you have a slightly higher mass density. I can swap strings. So that's what I did here. I don't know how that oscillator works, so I have to figure out what it's doing. So I took two different strings. They're both orange, and they have different mass densities. All right, so orange string 1, orange string 2, much finer. And I figured out what their mass densities are, and then I stretched them between the oscillator and the pulley. And then I just added weights until I could see an interference effect occur, right? So let me go ahead and take a look at the Excel spreadsheet I was doing that with. This always takes 2 seconds, and I know I look like a slack-jawed idiot while I'm trying to find the thing I'm looking for. Okay. So this is the first kind of orange string. This is the second kind, but I forgot to label it. And let me explain what my calculation does. Besides, forget to label important things. Okay, so for the first kind of string, I just figured out what its mass density was, right? Like I can put it on a balance and figure out its mass for a given length, divide it through, and I have a mass density in kilograms per meter. I can figure out what the tension I'm putting into the system is just by saying, all right, how much mass am I hanging off of that pulley? That's pulling the string. It's so hard to tell if you guys can see that string. That's pulling the string and putting tension into it. So tensioning mass, I just look at how much mass I have suspended on the pulley. Tension, it's mg, right? Mu, the mass density. Well, I just measure that by massing the string and measuring its length. V, this is the first derived quantity. This is the speed of a wave on this system. So as we increase the tension force, this thing goes up, right? Makes sense. It's a square root of T over mu. So it goes up. All right, lambda. How do I figure that out? Well, I keep adjusting the weight in the system until I see this thing oscillating. Oh, it's so hard to see. Hang on, let's try this. Absolutely cannot tell if that made sense. Let me go back to the main screen and we'll see if we can figure it out. Hang on a second. Okay, like I said, I always look like a slack-jawed moron for a second until I remember to do something with my face muscles. All right, so we have the string. You can see it's oscillating, right? I think you can see that. what I do is I just sort of walk along the string, count the number of nodes and antinodes that I have. And I know how many wavelengths are fitting into the length of the string then, right? Okay, so we'll go back to sharing the Excel spreadsheet, which is here. All right, I'm going to pause this for half a second so that I can plug my computer back in. Okay, I completely forgot what I was talking about. We have a knob we can adjust to change the behavior of the system, which is to change the tension force that we're putting into the string, thereby changing the speed of the wave as it propagates from one side to the other, which will change the timing with which that reflected wave arrives back and interferes, whether constructively, destructively, or somewhere in between. So I'm going to change the tension force in the system. Before, you were able to see that with this modest amount of weight put into the system, you can get a standing wave pattern. When I look at that, nothing looks like it's moving left or right to me, right? It just looks like it's going back and forth. Now, if I tinker with it, what will happen is I'll change the tension and I'll screw up the standing wave pattern. I'll lose the standing wave. So I'm going to do that. I need a third hand to do this. So hang on a second. Okay, so I think it's really hard to make sense of that. But what's happening is I'm putting my hand on the pendulum, not the pendulum, the suspended mass, and I'm changing the tension just by pushing on it or lifting it up a little bit. When I do that, I go from getting a nice, tidy, well-behaved standing wave pattern to something that's kind of messy and doesn't really add up to much. It just sort of looks like it's two non-synchronized waves colliding, right? So the behavior changes a little bit in time. I don't get something that's time persistent. Okay, so I can change T, and when I do so, I will be able to find a condition where I have a standing wave in the system. And I did exactly that. So let's go back to that spreadsheet and I'll talk you through it. All right, here we go. So tension, I just measure that by measuring the mass suspended from the pulley. So I know those two things. Mu, I measure that just by massing the string and dividing it by its length. V, I calculate it from the tension divided by mu, take the square root. Lambda, I measure that by looking and saying, okay, under this specific condition, when I've weighted the string up with this much mass suspended from the pendulum, I see exactly 3 lambda over 2 oscillations. So I see the string go zip, 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 right? I get 3 halves of a wavelength on the string. All right, well, if I know the wavelength of a wave and I know the speed of the wave, that means I know the frequency, because the speed of a wave, v, is equal to lambda times f. Speed of a wave is equal to the wavelength times the speed of the wave. So I rearrange that equation and I can calculate the frequency of the oscillator. And I did this with 2 different orange strings, right? First kind, second kind. Whatever I did to get a standing wave pattern, I measured those parameters and I calculated the frequency. And I always got the same frequency. This oscillator works just by saying, well, wall current is 120 volts AC alternating current at 60 hertz, at least in the United States. So 60 times a second, the direction of the current is going back and forth. It's oscillating. I'm going to use that to build an electromagnetic actuator that just switches direction back and forth 60 times a second. So that's how my oscillator works. Okay, it's not exactly dead on. Well, the biggest errors are things like, how did I measure the length of the string? I eyeballed it off of the meter stick built into that track. How did I measure the tensioning mass? I kept on adding and removing masses until I got something that I thought looked like it was creating a good standing wave pattern. I'm probably off by a couple grams here and there. How did I get mu? Mass to string divided by its length. There's some error in that because the string doesn't weigh a whole lot. So you got to put a fair amount on there. That gives you a chance to have a pretty large error in the length, maybe a few centimeters either way. Maybe your scale gives you only 2 really good significant digits, and the third one is kind of flaky. So those are the sources of error, but within a pretty small margin, I'm getting 60 hertz every time. So now I'm going to say I know that my oscillator wiggles the string back and forth 60 times a second. So I'm going to say that's now a known variable. So that's why I took away that question mark up here and just said, let's call it 60 hertz. Okay, now I looked at a string that I don't have any information for. It's the one that's actually oscillating right now, this green and white string. So I went back, and again, I applied a tension mass until I saw a standing wave. Like here, this tension gave me 2 full lambdas. So I saw bzz, 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 right, between the 2 posts. All right, that means I know that the wavelength is half of the distance between the 2 fixed points. So I've got my lambda, I've got my frequency, because we know that the oscillator oscillates at 60 hertz. So if I know the wavelength and the frequency, that means I know the speed of a wave on that system. So this is now a derived quantity. I've measured this. I presume that I know this from my prior experiment. I used it to calculate the velocity here. Well, I know the tension because I can just count up the number of masses I stuck on there and weigh them. I can mass them, excuse me, not weigh them. I can mass them. I can calculate what the tension in the string is. So I know the tension, I measure it. I know the velocity, I derive it from the wavelength and the frequency. That means I can figure out the mass density of the string. Okay, and I did that a bunch of times. So, just wrecked my knee. So putting a bunch of different masses on the end of the string and adjusting the mass a gram here, a gram there, until I got a really good standing wave pattern, I observed that the mass density of that string is 4 point something times 10 to the minus 4. So actually, let me just get an average. Oh, what did I do wrong? Who cares? 1 extra parentheses. Okay, so 4.5 times 10 to the minus 4 kilograms per meter, plus or minus something in the place after the decimal there in that representation. That's not bad, right? And it's a reasonable number because if I look at the other 2 strings I had, the very, very lightweight string was 5 times 10 to the minus 5 kilograms per meter. The more substantial string was 1.7 times 10 to the minus 4 kilograms per meter. So 3 times as heavy, right? 3 times as dense. All right, so those are known variables to me. I have that information. This string is much heavier and beefier, so I'm not surprised that it's twice the heavier of the 2 orange strings. That totally makes sense just based on me picking it up and holding it and thinking about, oh yeah, that's a more robust, it's a denser string, right? Okay, so that's the whole thing. This isn't easy to look at when you're staring through a tiny video screen, but maybe I can set this up so that we have 1 or 2 good patterns that you can observe. So let's go back and say, all right, to get the lambda case with this string, I need 590 grams on the suspension thing. So hang on 2 seconds and I'll set that up. Okay, so I now have, 590 grams on the suspended tensioning mass thing, right? So 590 grams goes up to the pulley. The string is approximately fixed at that point. At the other end of the string, it's tied to the oscillator. The oscillator is moving. That tape is so janky. The oscillator is moving, but just barely. And then I'm going to take a look at the pattern that's formed. Okay, that is as roughshod an experiment as I can possibly conduct. It's hard to see on the video, I know. So I'm going to go ahead and upload this. I think that kind of walks through the entire standing wave on the string demo / experiment / whatever. If you have any questions, please feel free to email me. I'll be happy to talk to you about it. Bye-bye.